this next problem says, and you need to read it kind of carefully, find the area in the first quadrant enclosed by the curves y equals x and y equals x squared over 4 below y equals 1. Okay, it's hard to know even exactly sort of where to begin, but okay, I kind of just know, so I'll start to graph this. And well, I only am interested in what's going on in the first quadrant, so I'll only draw the first quadrant, and then what now? Well, I have to graph y equals x. Okay, I can do that. There it is. And I have to graph y equals x squared over 4, and I guess it's when x is 2 that's going to intersect, sort of way up here at 4 or something. We're going to get no, at what am I doing? At 2. No. Oh man. When are those equal? 4x at 4. Yeah, that was right. At 4, when I plug in 4, I get 6 over 4 and 4. So this is going to be kind of look like that, I guess, is the thing that we're graphing. But this picture is sort of not the picture I want or whatever, because I'm only interested in the part of this graph which is below the line y equals 1. Alright, so, zoom in if you need to on your graph, or do whatever you need to do to realize, perhaps maybe even redraw this picture so that it's more clear what's going on. In fact, I'm going to do that right now, because I'm now sort of dissatisfied with this picture I drew, because once I read the problem very carefully, I realize that actually it's just this little green region that I'm trying to find the area of. So, okay, great. Let me now and what is this point right here? I guess I can figure out what that point is. This point is 1, 1, of course, but this point, I'm not really sure. I really need to solve the equation, when does x squared over 4 equal 1? And the answer is at 2. So this is going to be 2, 1, just fact. So this picture is sort of double bad, so okay, I quickly redo it. Woo! And we see that here's 1, 1, 2, and here's that, and here is the line y equals x, and here's this, and here's my parabola. Okay, so I think it is worth it. Sometimes people's pictures are so small that they can't tell what the hell is going on. That's 1, that's 2, and I now have completely figured out that the region that I want is this one. Okay, good. Well, now I'm just going to do this problem. Okay, but, and maybe I'll even, write, just so that I don't forget that this line is the line y equals x, and this line is this curve is the curve y equals x squared over 4. Okay, but I start to see that there's kind of a problem, and the problem is that there's no absolutely simple, straightforward way to do this anymore, because I have this region. I want to divide this region up into an infinite number of infinitely small regions so that I can add them all up. Okay, well, how am I going to do that? What we have been doing in the past is to just, partition the interval, pick a sample point, x of I star, plug it in, and get sort of 2 y values, and think of the entire region as decomposed into an infinite number of these little rectangles, and then just add them all up. Okay, but are you starting to see a problem here? I am, because it's true that this particular rectangle that I have drawn has a height which is equal to 1, which is that y value, minus x squared over 4. But that rectangle is not representative in the sense that it holds only for the interval from 1 to 2. But if I draw a representative rectangle on the interval from 0 to 1, now there's sort of a different formula, so to speak, which describes the height of that rectangle. Now the height of that rectangle is the difference in the y-coordinates between the top function, which is x, and the bottom function, which is x squared over 4. Okay, so you could simply, and there's just sort of no obvious simple way around that. One way you can put this is, there just is no single formula which will describe the height of one of these vertical rectangles, because different curves are describing the boundaries of this region as we sort of move horizontally along the region. So one way to solve this problem is to just accept that fact and to do it as two separate integrals. So this would be the integral from 0 to 1 of x minus x squared over 4, and then plus the integral from 1 to 2 of 1 minus x squared over 4. Okay, and this would be fine, and it would be correct, and you will get the right answer. There's even like a smoother way, which is you could find some sort of other area, and maybe you subtract out this triangle or something like that. Okay, but I'm not going to do this integral right now, or pursue that other idea, because the point of this problem is to inspire us to instead do something kind of wild. So what I'm now going to propose is that we free our minds from the bias of drawing our rectangles vertically. Who says we have to draw our rectangles vertically? No one. Integration is just the process of adding up an infinite number of infinitely small things. And here I have a region which has just been described geometrically. So who's to say that I need to divide it up into rectangles this way? Instead, hopefully you will see that if I partition this up into an infinite number of infinitely thin horizontal rectangles, then this is the sort of superior and more elegant solution to this problem, because now as this shape is the way it is, I can always say that this rectangle will have a length which is determined by the difference in two particular x-coordinates. And this point over here is always the x-coordinate of the point on the parabola, and this point is always the x-coordinate of the point on the line. And so with a particular expression, with a single expression, I can now represent the length of that rectangle, and I don't need to do it in two separate integrals. Okay, but this requires us to be very flexible in our thinking, because notice that this is the curve y equals x squared over 4. But if I am going to split this up into an infinite number of infinitely thin horizontal rectangles, then what I'm really doing here is I'm partitioning the interval from 0 to 1 up into subintervals. In other words, I'm partitioning the y-axis from y equals 0 to y equals 1. I am choosing a sample point, y sub I star, from the ith subinterval along the y-axis, and now I am going to express the length of this rectangle in terms of that y. Okay, so some people find this extremely easy, other people find it kind of tricky. What we now want is not an expression for the y value as a function of the x value, but instead we want an expression for the x value as a function of the y value. In other words, rewrite the relationship y equals x squared over 4 in terms of x. And of course, okay, we can kind of do this in our head, right? If you get 4y equals x squared, and so x is 2 root y. And so x equals 2 root y is just completely equivalent to y equals x squared over 4. They are both describing the relationship between x and y in the same way, which is to say that they are both descriptions of this curve. But you should think of the y equals x squared over 4 description of this curve as like a formula which takes as input x and outputs the y value. This is just like algebra 1 review. But x equals 2 root y is a formula which takes as an input a y value and outputs the x value. And similarly, of course, this curve can be rewritten as x equals y. Okay, all of this is to say that when it comes to describing the length of that red rectangle, has a length which is just the difference in the x coordinates of these 2 points. That point has x coordinate 2 root y sub I star, and that point has x coordinate y sub I star. In other words, for an arbitrary y value along the y-axis, when you plug it in, you get that output here and that output there, and so the difference between those 2 x coordinates is the length of the rectangle. Okay, I think everyone gets this. In other words, if I want to find all of those rectangles' area, I'm going to take the sum from I equals 1 to n of a bunch of rectangles. Those rectangles have area, or have length, 2 root y sub I star minus y sub I star, and have thickness delta y. And if I take the limit as n goes to infinity, then I get the area. Okay, so what, of course, does this become? It becomes the integral from 0 to 1 up the y-axis of 2 root y minus y dy. And now we just do it. Okay, so we do it. What's the antiderivative of y to the 1/2? You go up a power to 3/2, and you divide by that, so this becomes 4/3 y to the 3/2 minus y squared over 2, and that is evaluated at 1 and 0. And so what we get is 4/3 minus 1/2. The other ones are just 0. So whatever that is, 8/6 minus 3/6 is 5/6. Did I do that right? I probably did. Okay, and so that's the answer to this problem. Okay, but more generally, if you have some kind of shape that you want to find the area of, and if for some kind of reason your picture looks like this, say, then it's going to be very awkward and annoying to try to divide this up into vertical rectangles. So just feel comfortable enough that when presented with a geometric shape in which one can easily describe the dimensions of a horizontal rectangle, then simply, do that. And partition the interval, partition the region that way, if it makes the problem easier to do. Okay, good. That's it. Goodbye.